So this is going to be almost the exact same thing, only we replace summations with integral signs. So this will be from minus infinity to infinity x, f of x dx. And you can even do expected values as a function of x. So you go from minus infinity to infinity of x squared, f of x dx. And you can do the variance. This will be the integral from minus infinity. Well, actually, let's not do the minus infinity part. Let's do the expected value of the exact same formula. What is the formula for variance in the discrete case? That's the shortcut formula, which we'll get to the next one. Yeah?
X minus the mean squared.
X minus mu squared, yes. That would be the expected value. So what you do is you'd integrate minus infinity to infinity x minus mu squared f of x dx. And so the variance, now Josh, you can give me the variance. Shortcut formula is minus e of x squared. So we're going to go ahead and calculate the mean and variance for both of these, for all three of these. So let's go back to A so we can look at the picture. So let's calculate A, the expected value of x. Essentially, we're going to have to split this up into two integrals. So what's the first integral going to be? From 0 to 1 of 1/2 x dx. Very good. Plus 1 to 3 of 1/4 x dx. Okay, so add 1 to the power, x squared, divide by that power, so 2 times 2 is 4. Go from 0 to 1, 1/4, actually 1/8 x squared. Going from 1 to 3, 1/4 minus 0, plus 9/8 minus 1/8 gives me 1/4 plus 1, so gives me a mean of 5/4. That kind of makes sense. It should be between, well, yeah, so the average, the balancing point should be here at 5/4. Would balance that expression. Let's calculate the variance. And let's do the expected value of x squared. Here we go from 0 to 1 of 1/2 x squared dx plus 1 to 3 of 1/4 x squared dx x cubed over 6 plus x cubed over 12 from 1 to 3. I get 1/6 plus 27/12 minus 1/12. 2/12 plus 26/12 is 28/12. Which is 7/3. Am I calculating correctly? Okay, and so the variance then would be 7/3 minus 5/4 squared. Oh boy, 7/3 minus 25/16. Had this written down someplace, and I don't know where I wrote it. Can someone calculate that for me? Oh, 37/48. That's where I had it written down. Very good. All right, while we're here, I should talk about how you'd calculate the CDF for this, because this is kind of important here. The CDF from 0 to 1, well, first of all, for x less than 0, I get 0. Yeah. I get 0 if x is less than 1. From 0 to 1, I get 1/2 x, because that's the antiderivative of 1/2. I get 1/2 x. Now, the thing about the third one, though, is, what's the antiderivative of 1/4? 1/4 x plus a constant. So if I'm going to go from 1 to 3, what does this constant have to be for it to work out okay?
1/10.
It has to be 1/2, because if I plug in x equals 1, I've got to have 1/2 here. And if I plug in here, I've got to have 1/2 as well. So actually the C turns out to be, what'd you say? 1/2? That's not what I'm thinking. I think you want it to be 1/4. You want this to match up between the two. Yeah. So when x is 1, you've got a probability of 1/2, cumulative probability of 1/2. So if you plug in 1 here, you've also got to get a probability of 1/2. So what that means is that this has to be 1/4 x plus 1/4. So that you got to be a little careful there. Yes, Hallie.
Why does the 1/2 x not need a constant?
Oh, it should. When x is 0, I get 0.
Oh, it's just because when you plug those numbers in.
Yeah, I really should put a plus C there and show you that I needed a 0 there. But it's kind of hard to undo. It's like the problem of original sin, that you can't always go back and correct things, and then your sins of the past keep kind of multiplying and continuing on. But maybe you would allow me to put a little plus C and then cross it off. Can we do that?
Yeah.
Okay. Because Jesus does cancel our sins, right? All right, let's take a look at this one, 1 over y squared. Okay, let's find its mean and variance. And there's something interesting about this function. And it's as follows. The integral, or the expected value of, I think that was in a variable t, wasn't it? No, y. The expected value of y turns out to be the integral from 1 to infinity of y times the probability, which is 1 over y squared dy. And so I've got the integral from 1 to infinity of 1 over y dy. You take your value, x times your probability, your CDF.
Doesn't that come out to
It does. Very good, because what's the antiderivative of 1 over y? Natural log of y. And if you go from 1 to infinity, you really have to go take this limit as b goes to infinity. And this does not exist. So the mean doesn't exist. The same thing if you try to do the expected value of y squared. You'd have the integral from 1 to infinity of y squared, 1 over y squared dy, excuse me, and you get 1 to infinity of dy, which is also infinity. Diverges, does not exist, is infinity, whatever you want to say. So the variance does not exist for this function. The mean doesn't always have to exist for a probability distribution function. I mean, you have to really cook up some very strange, bizarre examples. In real life, you likely would not come up with it too much, but it does come up occasionally. All right, let's do the expected value of t, and I'm going to cheat a little bit because we already did calculate this antiderivative on the previous page. We calculated it as minus t e to the negative t going from 0 to infinity minus e to the negative t going from 0 to an infinity. Now technically, remember, these are improper integrals because we can't have an infinite width. So what we do is we take definite integrals and then have that limit of that upper bound go off to an infinity to get our value. Remember, in some sense, calculus is the study of limits, and integral is a limit itself. And so this is the improper integral is also a limit. What was that? We can use L'Hopital in this case because if you take, first of all, if you plug in 0, you're going to get 0. But if you take this limit as b goes to infinity of e to the minus b over b, what does that go to? Which wins out? Actually, I put this in the wrong order. I should have b in the numerator and e to the b in the denominator. This will go to what then? Exponential growth always wins out over linear growth in the long run. Of course, as John Maynard Keynes said, in the long run we'll all be dead. But so by L'Hopital's rule, this does go to 0. This one, what happens as e to the negative t if you go to infinity? This goes to what value? 0. And so you're just left with 0. Actually, you're left with 1.
Wait, yeah.
I didn't even integrate, rats.
Plug in 0 back in at the end, though.
Yeah.
No, when you plug in 0, did you get 1?
Yeah, I didn't. This is not the right problem because I was just calculating the CDF. Yeah, so we need to do the expected value of t. So, yeah, let's try that again.
Oh, I see.
Yeah, we didn't. I cheated, and see, this is the problem. Cheaters never prosper. You have to go through the long way of doing this. So I'm on the screen then. The expected value of e to the t will be the integral from 0 to infinity of t squared e to the negative t dt. This integral turns out to be 2. I'm going to show you a different method to find the second moment. And let's do from 0 to infinity of t cubed e to the negative t dt. And you could do the same one with this property as well. And some of you may not have seen this property before. It's kind of a nice thing for engineers sometimes. When you have to do multiple repeated, and there's some things in physics, particularly in quantum physics, where you have this e to the negative t power lying around that you have to integrate over and over again. So This is called the tabular method. And what you do is you have your u's and your v's, and you let t cubed take the derivative, 3t squared, 6t, and 6. And then v, you have e to the negative t, you integrate, e to the negative t, integrate, e to the negative t, integrate, minus e to the negative t. You integrate again, you're back to e to the negative t. And then you go across. You go down, 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 and down. And you alternate signs. So what you end up getting here is minus t cubed e to the negative t, because you multiply these two together. This one you multiply, but you got to put an opposite sign there, 3t squared e to the negative t. This one, you keep the sign, 6t e to the negative t, and this way you got to put a negative sign, e to the negative 6t. So this is sort of the tabular approach. If you got to do multiple integrations and differentiations, you can do this. This is just a nice thing to have in your back pocket at times. It's not necessarily you have to show it all the time, but then we could then find this to be that the expected value of t squared is equal to e to the negative t. Let's put the negative sign out front. T cubed minus 3 plus 3t squared plus 6t plus 6. Now, if we take this limit as t goes to infinity, what wins out? Exponential or this polynomial growth? So this would be 0 minus, well, we'll put in e to the 0, which is 1, and we get 6. So 6 is this integral. And so the variance turns out to be 6 minus 2 squared, or just 2. 2 squared. So there's just going to be a lot of integration that you're going to have to be able to do. One last thing.
Dr. K?
Yes?
So is the variance equal to the expected value then?
Yep, for this one it does. Doesn't mean it's Poisson, it just means that that's how it came out to be. One last thing, and that's the uniform distribution. So suppose I go from capital A to capital B, and this is a line. What do you suppose the height is going to have to be for this to be a probability distribution function? If I have a rectangle, what's the width down here? B minus A, so the height must be 1 over B minus A. So the mean just turns out to be the midpoint. Good old midpoint from high school geometry. That's great. The CDF, if I integrate this, will be like going from A to B. Up here will be 1. And you have a line there. I think you'll have some homework problems when that time comes. Remember, the homework will be due on Thursday, but you'll be able to turn it in without penalty on Friday. Okay, so tomorrow at noon, if you want to come, we'll do a review session. Make sure you turn in your test, take-home test, either the box there or the box underneath the things outside my office by 4 o'clock.
This is one group has turned into one take-home.
That's it, yeah. Okay. Anything else? Okay. Okay, see you tomorrow at 6:37 in 119. That's where we're doing one.
We're not having a class, I'm taking it at noon.
Yeah.
Yes, do we have class on Wednesday?
What was that?
Do we have class on Wednesday?
Yeah, we'll have class on Wednesday. No class. Yes, no class
on
tomorrow,
Tuesday,
but
okay.